Hi everyone. In section 1.5, a piecewise function was one function that could have different function rules for different subdomains. But how can we combine functions, multiple functions? Well, we can add, subtract, multiply, and divide them, as you might expect. For example, let f and g be functions. The function f plus g has a rule, f plus g of x, that can be defined as f of x plus g of x. You have similar rules for f minus g, f times g, and f over g. The domain of f plus g, for example, is the overlap or intersection of the domain of f and the domain of g. In order to be a legal input for f plus g, you have to be a legal input for both f and g. You have a similar domain rule for the others, except that with f over g, there's an additional restriction. The denominator cannot be 0. So for example, let's say that we want to consider f where f of x equals x squared and g where g of x equals x cubed. Well, you could consider a table for the function f plus g. Basically, you add the function values, you add the y coordinates to get the y coordinates you see in brown, and you might be able to consider point plotting. Some of you may have this skill, others may not. It's not really crucial to have this skill, but it's nice to have. Can you believe that basically the blue function, f, plus the red function, g, gives the brown function, f plus g? You're thinking in terms of adding y coordinates. Basically, blue plus red equals brown. If you can't really see that, don't worry about it. Here's an example where we're subtracting functions. Let f of x equal 4x, and let g of x equal x plus 1 over x. How do we get a rule for f minus g of x? Well, you can break this down as f of x minus g of x. F of x is 4x. G of x is x plus 1 over x, but remember, if you're subtracting something with more than one term, you must put grouping symbols. Or go ahead and distribute. At this point here, we can distribute 4x minus x minus 1 over x. A lot of people miss that minus sign. 4x minus x is 3x, and we can say that the function rule for f minus g is given by f minus g applied to x is given by 3x minus 1 over x on the domain of the function f minus g. But what is the domain of f minus g? Well, over here, what's the domain of f? The implied domain of f is all reals. It's a polynomial. But what about g of x? It's all reals except what number? It's all reals except 0, because we have to avoid a 0 denominator. So all real values of x, all real numbers, will be legal inputs for f and g except for 0. He's no good. He's the only one who's no good. So the domain of f minus g is a set of all real numbers except 0. And there are various ways of writing that down. Set difference form, set builder form, interval form. We skip 0. Again, you can multiply functions, but here let's consider dividing functions. And the domain question is more complicated. Let f of x equal 1, and let g of x equal x over x minus 2 on their implied domains. Find the rule for f over g of x, and find the domain of the f over g function. Let's write out the rule for f over g of x. It's given by f of x over g of x. F of x is 1. G of x is x over x minus 2. Let's simplify this expression. What is the reciprocal of x over x minus 2? It is x minus 2 over x. And what is the domain? What is the domain? Well, clearly from here in this final fraction, it must be the case that x cannot be 0. Otherwise, we're trying to divide by 0. In particular, notice that x equals 0 makes g of x equal to 0, the thing we're dividing by over here. So x equals 0 would produce a 0 denominator over here. X equals 0 makes g of x equal to 0. And we cannot divide by 0 down here. But wait a minute. Look over here. 1 over the fraction x over x minus 2. We have a problem if we're dividing by 2 down here. So x cannot be 2 either. But that restriction is hidden when you take the reciprocal. If you look at this final expression, it's not clear that x cannot be 2, but since 2 is illegal up here, it's also illegal over here. In particular, note that 2 is not in the domain of the g function. 2 is not in the domain of the g function. It makes the denominator 0. So x cannot be 2 because x equals 2 makes g of x undefined. In other words, 2 is not in the domain of g. Bottom line, you have a problem if you're dividing by 0. Up here, 2 is not in the domain of g because x equals 2 makes you try to divide by 0. But we cannot have the fraction itself be 0. X cannot be 0 either because we're trying to divide by g of x. So both 0 and 2 are illegal. This is a hidden restriction. We have to write this down. The domain of f over g in set difference form, and also in set builder form, graphical form, and interval form. We skip 0 and 2. Now, in addition to f plus g and f minus g, we could also consider things like 3f plus 4g, or pi g, or 0, or this thing. These are examples of linear combinations of f and g. Functions of the form number times f plus number times f. Number times g. And it turns out that the domain rule is the same as for f plus g. In particular, the domain of 3f plus 4g, for example, is the overlap, is the intersection of the domain of f and the domain of g. The only legal inputs for this guy are the legal inputs for this and for this. We like linear combinations of functions. There are nice calculus rules for these also. Next up, a more creative way of combining functions, compositions.